We often discuss on this show the vital roles black holes may play in humanity's future, how we may even come to live around them one day. But what if we already live inside one, and the whole universe is a black hole? Black holes are pretty weird, and given that, lots of weird questions come up around black holes. One question that sometimes comes up is if we live inside a black hole and how we would know if we did. We're going to discuss today why people think this could be true, as well as problems with the notion. Since we often discuss civilizations powered by black holes or living near or around them, we might also wonder whether it's possible for them to live inside one rather than just nearby. Now, there's some good and bad reasons suggesting we might live in a black hole, and also many good and bad reasons for why we cannot. One is that since we have black holes in this universe, then the universe itself cannot be one. I assume this is based on the notion that reality can only get warped into a singularity once per location, like in the TV show Babylon 5, how opening a hyperspace jump gate inside another jump gate makes it explode, and how putting a bag of holding from D&D inside another will rip a hole in reality. We don't really know that black holes don't operate that way, but we have no particular reason to think they do either. As for reality warping, we need to keep in mind that, while dead stars going supernova and ending up with a point-like hyperdense center called a singularity is one way to make a black hole, that a black hole in that context of a big spherical event horizon light can't escape from can be generated in other ways. Event horizons themselves can come from other events, and we definitely have event horizons all around us from the universe expanding, as we'll discuss in a moment. Now, we don't know that black holes form from dying stars are point-like in their centers. We just know that neutron stars, the ultra-dense dead star remnants left over from most supernovae, aren't quite dense and big enough to keep light escaping them, and that they are kept from falling into an even denser ball by neutron degeneracy pressure, the name of the force keeping neutrons from scrunching up more, and vastly stronger than the forces preventing us from doing so. Adding just a little more mass would overwhelm that force, and we speculate that it would then collapse either directly into a singularity, or possibly into a quark star or a Planck star. A Planck star is a hypothetical object from quantum loop gravity that can collapse no further under its own gravity by being held apart by being at the Planck energy density, which we think is the maximum density energy could have. 10 to the 99th power grams per cubic meter. A trillion, 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 trillion times denser than normal matter on our planet, but still not infinity. So a few notes here. First, singularities are a mathematical concept for poorly defined regions, and aren't in and of themselves terribly mysterious, just terribly inconvenient. The corners of cubes are singularities, for instance. So the notion of having one in the universe is undesirable, and in physics they represent a probable paradox which we dislike, so we tend to seek alternatives. Planck stars and the fuzzball from string theory are examples of that. Singularities are not necessary for either black holes or the Big Bang. A black hole is created whenever the energy density in a region gets high enough so that its escape velocity to the outside is higher than light speed. We usually call this mass, but mass is just one type of energy, and it's actually energy that generates gravity. A lot of hyperdense objects like neutron stars and whatever is in typical black holes is spinning so incredibly fast that much of their energy is angular momentum, for instance, and indeed most of the mass inside your typical proton or neutron is not the mass of its three nominally official and real quarks, but all the binding energy gluing them together, which we call gluons, and the more ethereal C quarks. It's not just a matter of density though, it's about having a place where the escape velocity from a region to outside is light speed or higher. For instance, our galaxy is possibly near 2 trillion solar masses, of which our sun is just one. If you packed all that into a region about a light year across, the average density would still be thinner than the air on Earth, but that condensed region would have an escape velocity higher than the speed of light. You would have a big black hole there around a light year across, but inside, initially anyway, it would be spread out so thin you couldn't even breathe. Which causes a head scratcher. A long time ago, our galaxy used to be a lot smaller. We say the whole universe used to be a dot or maybe a near-dot, an atom-sized blob down at Planck density, again 10 to the 99th grams per cubic meter. The galaxy would have been even smaller than an atomic nuclei back then, which brings up some tough questions. Why wasn't it a black hole? And if it was, why didn't it stay one? And why isn't the whole universe a black hole? That will take some explaining, but we need a correction first. While the more massive a black hole is, the less dense it needs to be, the present-day observable universe at its current mass, energy, and radius is too big for that, but it is really close, at least in terms of orders of magnitude, and the coincidence of that is, I'd guess, why folks tend to lock onto the notion that we might be living inside a black hole. It wouldn't matter if the universe was dense enough or not, as we'll discuss in a bit, and it definitely has been dense enough to qualify in the past, not just the Big Bang either, which does matter. See, we don't actually know how the Big Bang happened, or if it did, or how big it was, so to speak. The furthest back in time we can directly see at the moment is to when the universe was already a few 100,000 years old, and had finally expanded and cooled enough for photons of light not to be instantly absorbed. The universe before then, presumably, had been composed of ultra-hot matter like what you would find in stars, and quite a good deal denser, and at a certain temperature and density it transitioned, much as water transitions into ice or steam, into something more transparent to photons. Many of these photons have never been absorbed in the nearly 14 billion years since then. Even as the universe expanded, they are still basically everywhere. We pick photons of that age up from all directions, and we call this the cosmic microwave background radiation, or CMB. Everything earlier than this is speculative, but we can see the universe getting smaller and denser and warmer as we look further away, or further back in time. And we know what happens when matter hits a certain temperature and density, so it's not exactly a wild guess what happened. But pragmatically, we live the center of a universe 93 billion light years across, whose edges are composed of ultra-dense matter and the redshifted light it emitted. And everything about that statement is kinda sorta wrong. The topic is trying to explain what we can currently see, which is deep in the past, and what we can extrapolate its current state to be from that, and causes folks lots of headaches and misconceptions trying to discuss and contemplate it. But this is another strike against it being a black hole. Black holes are places you just can't see inside from the outside, because the light can't escape, but you can see the outside from inside just fine. We talk about ducking inside very big event horizons to try to hide a civilization as a possible Fermi paradox solution, and that's how that works. You can see the universe outside just fine, but you can't leave and they can't see you, kind of. That's exactly opposite of how the observable universe works. We can't see outside it. The cosmological event horizon of expansion is indeed an event horizon, but it's opposite to a black hole this way. Everyone has a bubble of space that is expanding around them that expands too fast for people or events at a certain distance or further from ever seeing or signaling each other. The light is moving fast, but space between those two objects is growing faster than the light can traverse it, so it never arrives. And most galaxies we see now qualify as that. No signal from us sent today could ever reach them. Only a smaller bubble of the universe is still inside that zone. The bubble is smaller than the observable universe, and we deduce that because the universe used to be smaller and we can still see light traveling to us from places back then that are too far away from us today for us to ever message them or vice versa. Now again, we do not know that the universe was an infinitely tiny dot in the past. We just know the portion we can see used to be way smaller, and you don't have to go back much further before we would have been dense enough to be a black hole. Again, at the time the CMB was formed, the observable universe was definitely dense enough to be a black hole. So why wasn't it one? Well, that's not something we can answer definitively because we don't know what's right outside the observable universe, but in all likelihood, it's more of the universe. The universe might be infinite and may have erupted from a smaller but infinite Big Bang, of which our universe was a tiny dot, and indeed would be even if we compared it to that now infinite Big Bang. Or it might be just a little bit bigger than our observable portion. We not only don't know, but don't know any way to find out. If it were infinite though, then the black hole issue is resolved. Much as the infinitely old steady state model pre-Big Bang resolved it, gravity is generated by everything, so a big dense fog of infinite size has got its individual bits all equally pulling in every direction out to eternity's edge, so no collapse. You could have localized collapses in spots that were denser than their peers, just as we have now, and indeed that could have resulted in primordial black holes, but nothing across the entirety of things, just local bubbles, which would then collapse to something denser too, but we'll come back to that as well. We also need to keep dark energy in mind, which, as best as we can tell, is the tendency of the universe to pop out tiny new little bits of space everywhere all the time, presumably right inside you and me, and over a distance of light years this results in everything moving apart from each other in a noticeable fashion, but one easily countered by gravity. Double the distance, double the expansion rate though. Only at extragalactic scales is this expansion so great that even the massive gravity of entire galaxies can't bind each other together anymore, as gravity weakens with the square of distance, while expansion speed rises with distance. Move two galaxies 10 times further apart, and the expansion speed between them from little bits of space-time emerging from parts unknown will go up by a factor of 10, while the gravity fighting that will have dropped by 10 squared, or 100. So trying to move apart 10 times faster, and now with only 1/100th the gravity trying to bind them. So a black hole forming at that scale gets to be a pretty dubious thing, and the biggest ones known, like Phoenix A and Ton 618, are about a light month across, not a light year, let alone millions of them. If we did hypothesize a mega huge black hole of galactic scale, made of whole superclusters, then we might imagine that its event horizon would be smaller, as dark energy near its edge might significantly cut into its gravity. So too, in terms of ways to escape a black hole, your best bet might be some way of ramping up dark energy expansion near you, using some unknown clock tech. I should also note that gravity travels at the speed of light. As an example of how that can make things unexpected, the force distant galaxies exert on us is not what it should be for their proper modern distance, because they were closer back then, much as their light was. So if a black hole was suddenly teleported into your area, it takes a few moments for that effect to percolate out. There are other issues with our region of the universe, the observable universe being a black hole, but requiring more of a deep dive into both general relativity and quantum, and it still doesn't say it's impossible, just that we have no real reason to think that we do. So we'll limit discussion to just what we covered and instead ask if it would actually matter if we were living inside a black hole. Again, we have to demystify black holes away from what movie science has portrayed them as, and I hate to say it, but physicists are guilty of this too, because we tend to hype them up as mysterious and awesome to get folks interested in them and physics in general, and they are awesome and mysterious, but it's still hyping, and combined with that movie science gives people the idea that black holes are dangerous to be nearby, and maybe even portals to other universes. Neither is necessarily untrue, but your typical natural black hole is an object several kilometers across, not several million kilometers across like the star that produced it, and those are so immensely hot that you'd be incinerated a billion kilometers away, whereas a black hole is merely dangerous in terms of radiation because they tend to acquire accretion disks of matter that hasn't fallen in yet. Indeed, in reality it is very hard to fall into a black hole. They are not safe, exactly, but they're far less dangerous than the stars that birthed them, and their gravity is not in any way special. It's only because they are very dense that it's possible to get so close to one that the diminishing gravity with distance is at such a scale that your head could be torn from your feet simply because gravity at your feet is much higher. The scientific term for this is spaghettification. This still requires being ultra close to one, far closer than you could fly to any star, and indeed this effect is much smaller on bigger black holes. Very large ones would not have this at their event horizon. Further down the well, they still could spaghettify you if they are singularity or ultra-dense anyway. Presumably. It's impossible to really discuss the inside of an event horizon with any certainty since the math gets tricky and we can't see inside to gather data. There's nothing special about the event horizon incidentally, as they shift based on your speed. Black hole horizons appear smaller if you're moving toward them and bigger if you're moving away, and time does not stop there. There's just a frozen moment where a photon could be thought of like a spaceship leaving a gravity well, but not fast enough, akin to orbiting a world. Don't assume that means there's photons stuck in one place though, any more than satellites hanging static around a planet, which is never stable in the long term, part of why I'd be very dubious about building a stable arrangement of matter that could be massive enough to form a black hole and not actually crush itself down, but on paper at least, and depending on the model, you could pack a lot of stellar objects into really tight orbits of each other like a Dyson swarm, but made of stars rather than around one star. We are still a little unclear on the specifics of how two large merging objects like neutron stars or black holes undergo frame dragging and ring down to create a single object with a single event horizon, but basically if two black holes touch event horizons they form a new black hole with a diameter equal to those two black holes' diameters combined. And we would expect that if we brought a bunch of black holes or neutron stars into a Kepler rosette or similar stable orbit that we would get a big black hole with no center, and in the case of neutron stars, no singularity. You could go live in there safely, kinda, but could not leave. For today's purposes, we are going to bypass discussion of naked singularities and the cosmic censorship hypothesis, but there are some potential problems with building a black hole from a stable ring of dense objects rather than a big collapsing sphere. Again, the necessary density of a black hole in terms of event horizon drops off quickly with size. A black hole 10 times more massive has 10 times the radius, but 1,000 times the volume, so only 100th the density. By the time you get to tens of millions of solar masses, those bigger known black holes we find at the center of galaxies like Ton 618, your density is down to that of your typical rocky planet, and at 135 million solar masses, it's down to the density of water, and by a billion solar masses, you have a black hole 6 billion kilometers across whose density is equivalent to that inside something like a Niven smoke ring, which might be imagined as an asteroid belt that orbited in air, not space, so critters could fly around between islands in the sky around their sun, or inside their black hole. 10 times more massive, 100 times less dense, and even 10 billion solar masses is less than 1% of our galaxy, which means you could probably create yourself a large initial black hole that you built a shell around to keep matter from falling into and serve as a big black hole powered light bulb as a fake star, then pack vast amounts of artificial planets and habitats around until the interior disappeared and eventually it spread to everyone there. Again, I'd be very dubious about pulling this off without causing everything to fall down into the black hole in the basement. I can think of some reasoning for why it might be impossible, and a better cosmologist might be able to say yay or nay, but it's one possible alternative fate of the galaxy, in line with a Birch planet or superself, which is where you build a massive spherical shell or several concentric ones around a supermassive black hole. See the Megastructural Compendium or episodes Mega Earths or Colonizing Black Holes for more discussion of that option. Going back to if we might live inside a black hole, I said a bit ago that modern cosmology doesn't say we're in a black hole, but doesn't 100% preclude it yet either. However, that's a bit disingenuous. We have no idea where the Big Bang came from, and as we discussed in our episode on the Big Rip, it is even possible we're in constant Big Bang mode, where new universes constantly expand from older ones like branches on a tree. Only in a Big Rip case, more like a new universe for every atom that existed in the previous one. And there we suggested hiding inside black holes as one way to survive a Big Rip scenario, and one that wouldn't violate the Fermi paradox situation either, of wondering why a race from a prior universe hadn't colonized all the observable universe already. That's not the only cosmological model that results in new universes bursting out from tiny points either, and gives us the whole notion of black holes and baby universes, which is also the name of a collection of essays by Stephen Hawking that came out in 1993 when I was 12, and I remember the local librarian had reserved me a copy knowing I'd want it, and I remember barely understanding half of it. And I got the idea of them as portals to other universes, or making new ones by white holes, but I didn't get where whole universes of new matter were coming from. It was what I asked my first physics professor a few years later, along with countless other questions, which probably explains his somewhat exasperated answer saying, "I have no idea, Isaac. Most of us in this field don't learn much cosmology beyond the basics." And that was early 1997, so dark energy wasn't even a thing yet, but over the years I noticed it as one of those questions people ask that rarely gets answered for them either. So if you're curious, there is no specific answer. Sometimes the assumption is just that our universe was on the downhill side of a very massive black hole in a much larger universe, and itself spawns only smaller universes the mass of that black hole, which would then presumably slowly evaporate back up as Hawking radiation lowered the mass of that black hole and that baby universe, essentially spitting a new universe out then sucking its matter back in. Others argue that once created, the connection is lost, and under general relativity, energy and mass is not required to be conserved at that scale anyway. Plus, in a very real way, a black hole is a separate universe, at least as much as the unresolvable universe or Hubble volume is. And here's a key point. The universe is gaining in energy. We don't know where dark energy comes from, and it could be spilling from some other universe like ours, just bigger, and might eventually slow or stop. Or it could be from someplace very different and be an effective infinite or accelerating well. Nor does it necessarily need to come from anywhere. We tend to view the Big Bang differently these days, less of a single moment of a singularity suddenly expanding, and more the beginning of a rapid and constant state of inflation. There's also multiple versions of black holes making new universes in terms of how it might operate. Legendary physicist Lee Smolin put forward a hypothesis of cosmological natural selection, where new universes spawn inside black holes with slightly different values of physical constants, like a higher or lower speed of light or gravitational constant. Universes whose parameters are optimal for generating black holes then dominate the multiverse, hence the analogy with natural selection in biology. Smolin proposed the idea of a falsifiable alternative to the anthropic principle, and it did result in some strong predictions for things like maximum neutron star mass, where absorbed values were on the edge of the prediction. The hypothesis has seen some revival since its first publication in 1992, and the jury is still out. And honestly, probably will be for a long time. As I mentioned earlier, many of these ideas are next to impossible to test, and may be outright impossible. A singularity might spawn a new universe, less in the sense of a bridge forming to the prior one to drain matter and energy across, and more as forming a new node or poke in reality or balloon in which inflation driven from some greater elsewhere can begin, like a big rip. In that context, it's entirely possible that we do live inside a black hole, though the term inside gets rather iffy, as it's inside another, and that one inside another, and that one inside still another. Once you officially put infinity on the table, there is no real need to waste time worrying about conservation of matter or space or time or energy beyond local affairs. And for that matter, we often talk about time slowing in black holes, and so dumping huge amounts of matter through one over eons on this side into a brief moment on the other wouldn't be a problem either. Don't worry if this all feels confusing. It really is. To me too, and I have friends who specialize in this area of physics and cosmology and who feel much the same after decades of study. It is weird and counterintuitive, with lots of unknowns and probably lots of unknown unknowns too. Ultimately, the quest for knowledge must continue at least a little while longer, and it does seem like our future will be very dependent on what we learn about them. I often worry that black holes will turn out more mundane than we expect, but for now they offer a glimpse of a future where we might be able to power civilizations of breathtaking scope, maybe beat thermodynamics and entropy, and possibly even create our own new universes, or survive the death of this one. That's an awful lot to expect from something so tiny, but then again, this is what black holes are best known for, getting an awful lot of stuff into something very tiny. As I've mentioned in passing, one of the other hats I wear outside of this show is being chairman of the Board of Elections for my area under the Secretary of State, and we work a lot with the Department of Homeland Security on cybersecurity for elections and election infrastructure, and it's constantly shocking how frequent and inventive thieves and hackers have gotten. Our sponsor for today's episode, NordVPN, asked me if I had any personal experience with some of those newer attack methods, and it reminded me when I was actually at an election conference where cybersecurity was one of the topics, and someone I knew was trying to find a Wi-Fi connection with every Wi-Fi network at the hotel jam-packed and slow, and probably narrowly avoided what is called a man-in-the-middle attack. And these are very common in hotels and coffee shops. Imagine going to a coffee shop and connecting to a free Wi-Fi named Coffee Free Wi-Fi, which looks totally normal and not out of the ordinary. However, turns out the Wi-Fi is actually being hosted by a random person trying to impersonate the free Wi-Fi access, While you enjoy that free Wi-Fi, he has access to your data, as he created that same network you're using on his own PC. Thus, when you connect and go to the banking system you usually use, the information then flows via the man-in-the-middle imposter device, and he can capture the information you entered. To protect yourself, always check for lock and HTTPS near the destination URL, and use NordVPN, as it will encrypt your data flow no matter if the destination connection is secure or not. NordVPN has tons of alerts and protection features to help protect you from attacks like phishing or ransomware or malvertising, and warn you of the clever tricks thieves use these days, along with educational materials to help you understand and avoid threats. That is in addition to having a great virtual private network that encrypts your data and can send it through any of their 5,400 servers in 59 different countries to protect your privacy and keep you safe. You can check out their website to learn all the benefits NordVPN offers. Just go to nordvpn.com/IsaacArthur to get a 2-year plan plus 4 additional months with a huge discount. It's risk-free with Nord's 30-day money-back guarantee. So we are almost the end of the year now, with Christmas this weekend and New Year's just 9 days off, and we still have one more regular episode looking at humanity's future and transhumanism next week. But we have also moved our live stream this month to Saturday, December 31st, 4 p.m. Eastern Time, right before New Year's. After that, we'll head into the new year to look at interstellar colonization strategies. If you want alerts when those and other episodes come out, don't forget to subscribe to the channel and hit the notifications bell. And if you enjoyed today's episode and would like to help support future episodes, please visit our website, isaacarthur.net, for ways to donate, or become a show patron over at Patreon. Those and other options, like our awesome social media forums for discussing futuristic concepts, can be found in the links in the description. Until next time, thanks for watching and have a great week.